You will adjust, and you'll do just fine, right? You'll do just fine. So we can go through some of the free response if you like, or we can, if you have particular questions, or we can just sort of skim through the multiple choice, and whichever ones peek out at you, we can do those. There are some other free response. We did this one in class the other day. I think we did all three of these in class, didn't we? Yeah. There are some other that are really similar to this, so I would practice those, and we can look at them too. But the free response is going to be just like this. I'll change the numbers. I think I changed the figure on this question with the electric field. I think I made it so it's like a capacitor, but it looks much the same. It's just it has the electric field lines, and you have a charge moving from one side to the other. The way that you work it is exactly the same, and the information that you're given is exactly the same. It's just the numbers are different. So you want to get those 8 questions. That's 8. I mean, man, that's like almost a third of your exam. You want to get those 8 questions without any problem at all. And, you know, try to get to a point where you don't even really have to think about them that much, that you just know how to do it right away. If you're at that point, if you really understand and can do these 8 questions, then that really helps you in a lot of the other parts of the exam too. Are there particular questions that y'all want to look at? Yeah.
So like for 2018 on number 7, the ones that are like set up like that, sometimes you get like either an E1 and an E2 and subtract them, or depending on what it adds, you'll get an F1 and an F2 and subtract them. I'm just wondering, like, how do you know when to do, like in this problem, you have to do the hypotenuse? Is it because it asks for the electric field, or is it because how E2 goes like to the negative x axis?
Yeah, so he asked, sometimes we subtract or add E1, E2, those sorts of things. In this case, what we have is we have 2 vectors, E1 and E2. E1 is due to Q1, the minus 8 nanocoulomb, and E2 is due to the 2 nanocoulomb charge. That both of those are on axis. And so that makes it an easier problem because you don't have to deal with finding the x and y components. So in this case, when I have these 2 vectors like this, I can redraw. I'm going to redraw E1 like this. Then to find the resultant vector, I just take the hypotenuse. But what you're also referring to is that sometimes we have vectors where one is on axis and one is off axis. And in those cases, we have to find the components of that vector that's off axis, and then we have to subtract the 2 vectors, or add, if they're in the same direction, the 2 vectors that are on either the x or the y axis. So we would subtract these 2 vectors here and here. I think that's what you're asking. Is that what you're asking?
Kind of. So like in that problem, if E2 is going towards positive, so I guess if positive is negative, you would just subtract the 4.5 from each other, and you wouldn't have to?
Oh, no. So if E2 was going in this direction, that's what you're asking? Mm-hmm. No, it'd be exactly the same. To find the magnitude, you would be finding this vector right here. But it would be the same. It would just be in a different direction. It would have the same magnitude, just a different direction.
So are you ever going to have to subtract E1s and E2s like you do with force power?
You could, yeah. So like if I had a configuration of charges, say a plus charge here, what would it be? And a negative charge here, and I ask you, what is the electric field here? We'll say this charge 1, this charge 2. The electric field due to charge number 1 is in this direction, and the electric field due to charge number 2 is in that direction, E1, E2. And so to find the net electric field, it would be E1 plus E2, because they're in the same direction. Is that what you were asking?
Kind of, but I think I get what you're saying.
Okay. Your free response is going to be off axis, one of the vectors. So there will be some addition or subtraction of the components of the vectors. All right. What questions? Any particular questions, or you want me to just skim through? Yeah. Of 22? Yeah, I think that was last year. So. Oh, okay. Yeah. So we've done this where I find the potential at a given point, but here, and just sort of switching it around a little bit and asking the potential here is 0. So what is this charge equal to? Well, the potential is equal to KQ1 over R1 plus KQ2 over R2. And so I'm saying that 0 is equal to 9 times 10 to the ninth. Q1, I don't know, I'm trying to figure that out, divided by the distance, which is 5, plus 9 times 10 to the ninth, times Q2, which is 9 times 10 to the minus 9, divided by the distance, which is 3. So I get some cancellations here. These cancel. This leaves that with a 3. And so that gives me something plus 27. So I get 0 plus, or 0 equal to 9 times 10 to the ninth Q1 divided by 5 plus 27. And then, you know, I could look at this at this point. I could solve that for Q1, and that's not that hard. But I can also say, well, I know that Q1 has to be positive or negative. Which is it? Negative. It has to be negative, so I can get rid of D and E. And then I have 5, 15, and 25. Now, I know that this side needs to be negative 27, and this side is 27. So you know what Q has to be here to make this into 27? That is, I have to have 3 times 9. So what must Q1 be in order to get a 3 right here and get rid of this 5? You know, do that math in your head. Does that help you, or does that just confuse you more? It has to be what? It has to be 15. That's right. Because 15, if Q1 is equal to 15, 15 divided by 5 is 3. The nano cancels out with that, and I get 3 times 9, which is 27, which cancels out with the positive 27. So it has to be A is the right answer. But you could go through and solve this. I'll just finish right quick. So you could go through and solve it algebraically. So I'd have minus 27 is equal to 9 times 10 to the ninth times Q1 divided by 5. I cross multiply, so I get negative 27 times 5 divided by 9 times 10 to the ninth. So that's 3, that's 15, negative 15 times 10 to the minus 9. Yeah, Gavin?
How did you cancel nano earlier? Right there, you're still.
Yeah, so I said that this value would cancel if it were nanocoulombs, and they all are nanocoulombs. That's why I use nano, because it gets rid of those 9s, and you don't have to deal with them anymore. Okay. You'll see that on all my problems, all the math usually works out that way. It's just to make the numbers easier for you to work with, because I want to know that you can work with numbers, but that's not really my goal. I want to know that you understand potential and fields and forces. Yeah, Carly?
Exam for spring 19, number 12. In the question, it says that it's a negatively charged rod, but then the rod in the picture is positive. Can you just work it out? Like, I don't know what the actual.
Okay, yeah, I must have had a mistake. I'm sorry. So 2 uncharged metal spheres are in contact, and a negatively charged rod is brought close. Well, let's say it's positive. So if it's positive, when it's brought close, the negative charges are all going to move over to this sphere. They'll be attracted. And then that's going to leave an excess of positive charges over there. And then the 2 spheres are separated. So we get a separation between those 2 spheres. And so that's what you're left with, that the left one is negative and the right one is positive. If it were a negatively charged rod, it would just be the opposite. So if this was negatively charged rod, then you would get negative charges over here and positive charges over here. But it's just exploring an idea that these like charges are going to repel. So our opposite charges are going to attract. So these positive charges will attract electrons over to this sphere. And then when you separate them, you get that charging by induction. That's what we call that. as opposed to conduct. Okay? Occasionally there are mistakes in the videos. I'm sorry for that. I can't go back and check. They're not easy to check. But if you have a question, if you think there's a mistake, send me an email. Or often if there's a mistake, I'll put it in the comments section or in the description of the video. I'll say it's like 220 or whatever. There's a mistake. That's usually what I do. Yeah.
Okay, going back to the first question I had. So if we look at on spring 16, number 11, it's like asking for the same thing, but on this one, you don't have to find the like hypotenuse. I'm just trying to figure out like what's the difference between this problem and the one that we did when we started.
For number 11, you didn't have to find the hypotenuse?
I think you just did one E1, like you just did K of 2 times 10 to the negative 9 over 3 squared, and you get like 2.2. I mean, I might have worked that wrong, but I mean, I ended up getting it right.
Let's just do it. So you have to use the Pythagorean theorem. I have an electric field in this direction due to the 2 nanocoulomb, and in this direction due to the 1 nanocoulomb. I'm going to draw it actually correctly, where one vector is half that of the other, because the charges are half, one is half the other, and the distances are the same. So I can calculate, I'll call this 1. E1 is going to be 9 times 10 to the 9th, 2 times 10 to the minus 9, divided by 3 squared, cancels, 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 cancels. So that's 2 newtons per coulomb. And then E2 is 9 times 10 to the 9th, 1 times 10 to the minus 9, divided by 3 squared, cancels, 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 and that just leaves 1 Newton per coulomb. And so I get, this is 1, and this one's 2. So in order to find the resultant vector, the resultant vector is right here. I have to find the x component and the y component, which I already have, 1 and 2. And then it's going to be the square root of 1 squared plus 2 squared, which is 2.2. Is that what you meant?
I guess I just worked out wrong.
Yeah, you have to use the Pythagorean theorem. There's no subtracting because there's only one component on each axis. Or adding vectors. You're just using the vector addition to find the.
And then for the problem after that, you just did the tangent inverse of.
That's right. Yeah. To find this angle right here, theta is the inverse tan of 2 over 1, which is something bigger than 45 degrees. It must be 63, yeah. Y'all see how I knew that it must be bigger than 45 degrees because the y component is bigger than the x component. So that vector is below the 45 degree mark.
Why wouldn't you do the f equals just the k times q1 q2 over r squared? Why wouldn't you do that like twice? Where it's like the difference between a and plus 2 and the difference between
I don't understand. And you just repeat. I'm hearing your words. I'm just not understanding. Like, why aren't there 2 q's in the equation? Why is it not kqq over r squared? Yeah, so you're thinking force, right? Yeah, so we're looking here at electric field. Electric field, remember, is kq over r squared. But you're thinking force, which is kqq over r squared. But at the electric field, I'm looking for the electric field at this point, and there is no q right there. So I couldn't, there is no force acting right here. There's only an electric field. Does that answer your question? Yeah. Be careful. Those equations, they all look really similar. All 4 of them. Field, forces, potential, and potential energy. They all look really similar. So even if you have them right in front of you, I find that students can sometimes get them mixed up. So just be careful with that. Practice will help you with that. All right. Other particular questions? Yeah, Gavin?
I'm having trouble with the response.
Okay. Let's go to the spring 21 exam. Since I've already done the spring 22 in class, is that okay? It should be similar. Yeah, number 4 is similar, but we'll go back and look at that because I did ask another question. But this is number 4 from spring of, oh, this is 19. Now let's go up to 21. Here we go. A proton moves from a potential of 8 volts to a place where the potential is minus 2 volts. So I have this proton moving from this point over where V is equal to 8 over to this place where V is equal to negative 2. Now, remember that potential is energy over charge. I'm going to call this kinetic energy over charge. And so if I want to know the kinetic energy, that's just equal to the product of Q and V, or in particular, a delta V. In this case, moving from 8 to 2, my delta V is going to be 10 volts. I know actually the delta V is minus 10 volts because I'm doing negative 2 minus 8. But here I'm just looking for the speed, so that doesn't really matter. Since I'm looking for the speed, I can just forget about the signs. So I have then 1/2 mv squared. You do need to know that, okay? That's not on the equation sheet. Is equal to Q times delta V, where little v is the speed and big V is the potential difference. Now I can solve this for V, which is going to be 2Q delta V over M, square root of that. And I plug in my values for this. That's 2. A proton is 1.67 times 10 to the minus 27. That's on your equation sheet. Your delta V is 10 divided by the mass, which is, oh wait, no, I did the Q wrong. This is 1.6 times 10 to the minus 9. Excuse me, they look really similar. And this is 1.67 times 10 to the minus 27. And so that would be your speed. Now, that other question also asked, what is the electric field? Because there is an electric field that runs from between those 2 equal potential lines. The equal potential line, by the way, would run perpendicular in these directions. This one on the left, this would be an equal potential line of 8 volts. And this is an equal potential line of minus 2 volts. So I have this electric field going between these 2 equal potential lines. And I ask, what is the magnitude of the electric field? And I know that this V is equal to EX times X. That is on your equation sheet. Actually, I think there's a negative right here. But again, I'm just looking for the magnitude of the electric field, so I'm not really worried about the signs. So my V is going to be 10 volts equals to EX times whatever. That is just the magnitude of the electric field. I'm just going to leave that X off. Times whatever the distance is. Let's just say that X is 2 meters. I don't know, just making up a number. Then E would be equal to 5 newtons per coulomb or 5 volts per meter. That's also a unit for that electric field. So there are 2 parts. Here I just had the 1 part, but there were 2 parts in the previous test where it's dependent upon this relationship. That V is equal to the electric field times the distance that it travels. This is on your equation sheet. But we didn't use that. No, we used it quite a few times, actually. We did this a few times. Is that okay, Gavin?
Yes, sir.
Be prepared for that, okay? You're going to see it tomorrow.
10 divided by 4.
10 divided by 2.
Depending on the distance you give.
I just made up that distance. 2 meters. I mean, 2 meters is kind of big, right?
What's the thermometer?
Put down a 0.2 on there. All right.
What happened with the 1/2?
Yeah, so the 1/2 here, I was solving this for Z, for little v, so I brought the 1/2. I multiply both sides by 2. And so that's why I get this 2 times Q delta V. And then I divide by M to get the M over to this side, and then I take the square root of the whole thing. I was just solving this, but if that confuses you, sometimes students feel more comfortable by putting in the numbers up here and simplifying the numbers. If you do it that way, there's sort of more places for errors, but that's okay if you do it that way. I understand. Does that answer your question? All right. Other questions? I'll sort of skim through some of the multiple choice here. You can sort of take a look. You're going to see, your test is going to look a lot like this. I have a spreadsheet that, yeah, like it. Mm-hmm. Okay, so a couple things to note here. First of all, the 5 nanocoulomb charge doesn't affect the electric field at that position. So when I'm considering the electric field at this point, I'm only considering this charge and this charge. And then notice that if I draw my electric fields like this, that they will have components that will be in the x direction and in the y direction. And so one of them will have a component in this direction, another will have a component in that direction, and then I'll have components in this direction and this direction. So let me put some labels on this. We'll call this E1, E2. This would be E1X, E1Y, E2X, and then this would be E2Y. What I want you to recognize is that these two X components, that they cancel one another out. So the total electric field vector is going to be twice E, the Y component of E, because both of these charges are the same, and they're both the same distance from the point where you're trying to find the electric field. So what you need to do is to find the magnitude of one of these electric fields, take the Y component of it, and then just double it, and then that'll be the answer. So let's first just figure out we'll just say we'll calculate E1. That is K, 9 times 10 to the 9th, times Q, which is 10 times 10 to the minus 9, divided by the distance squared, which is 3 meters squared. That cancels, 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 and I'm left with 10. Now, probably if you did this and you got it wrong, probably this is where you went wrong, is that I'm looking for the Y component, but I want you to notice that that angle 60 degrees is measured from the Y-axis. Remember last semester, whenever we're finding components, we always measure angle from their X-axis. So in order to find the Y component here, EY, there are two things you could do. You could say 10 cosine of 60, even though that looks like an X component to you, because we always use cosine for our X component. Or you could say 10 sine of 30. Both of those are equal to the same thing. And then when you do that, that's what, 5, I think? And then you double it, and so the answer is 10. Oh, did you not double it? Oh, the cosine thing. Yeah, that was one of the hard parts. So, does that come up on this exam? I don't remember me doing that, but I could have. Yeah, you should always, well.
So I could say the angle at the bottom of the 10 is 30, and then you find your Y.
Uh-huh. Really, it's this angle, right? You could use that angle, which you know is 90 minus 60 or 30. Always measure your angle from your x-axis. Or, remember that cosine has to do with the adjacent side. And since this component is adjacent to the angle, then I'm using my cosine. Cosine is adjacent over hypotenuse, right? So, whichever of those works better for you, I'm okay with.
And why do you double E1?
Because there are two charges. Right? There's this charge and this charge. And so when I was calculating EY to find its 5, that's just one of these vectors. But really there's two of these vectors. That's why I double it. That was a tough question. I remember that question when I gave this test. It was tough. It's stuff like this that makes the test hard. Vectors, there's lots of stuff to go wrong in vectors, and I expect you to know vectors pretty well because we had a whole semester of vectors. So, and it's also our last chance to get this kind of vector math in. You won't see it again this semester.
Did you do the next one?
Sure. All right, let me cancel. Let me erase all this.
I set it up like that, but I ended up getting 4 instead of 2.
Oh, yeah. Okay, so I would love for y'all to just think about this problem and not actually do any calculations. Because I know that I want the electric field, I'll call this charge 1, and I'll call this charge 2. I want the electric field E1 to be equal to E2 in order for that electric field to be 0. But notice that Q1, or Q2 rather, is 9 times the charge of Q1. 9 times. Now, if Q, remember, E is equal to KQ over R squared. So I have a factor of 9 up here. That means that I'm going to have a factor of 3 down here in order to make the electric fields the same. In order to get the same electric field from both of these charges, one of which is 9 times the charge, that means that this charge has to be 3 times as far away. But this charge is 2 meters away. That means this charge has to be how many meters away? 3 times 2, or 6 meters. And if this distance is 6 meters, that means that X has to be 4 meters. I would really love for y'all to work it that way. I find that that's a lot easier, and it shows a better understanding of the electric fields. Okay?
Why did you do 3 times 2? Oh, you're doing 3 times the distance it already gave us?
The reason I did that is because this charge is 9 times this charge. So I get a factor of 9 here. So I also have to have a factor of 9 in the denominator. But it's squared. The R is squared. And so to get a 9 in the denominator, I triple the distance. So I get 3R, but 3 is squared. So that gives me 9 over 9. So my electric fields are equal then. I really prefer you work it that way. The harder way, I don't know if it's harder, but the way that has more places to go wrong is just to say E1 is equal to E2. That is to say that K times Q1, which is 2 times 10 to the minus 9, divided by the distance, which is 2 squared, is equal to K times 18 times 10 to the minus 9, divided by X plus 2 squared. And then I can do some cancellations here. That makes the math a little easier. That goes away. That goes away. This goes away with one of those. And that's it. So I get 1 over 2 equals 18 over X plus 2 squared. To think back to algebra, but this is actually, it turns out to be not that hard because 18 times 2 is 36 is equal to X plus 2 squared. I square root both sides. 6 is equal to X plus 2. So X is equal to 6 minus 2, or 4. All right. I wouldn't, if this wasn't a number that was easily square rooted, it would make it a little more difficult to solve. But I'm not going to give you like a really tedious algebra problem. That's not my goal. So if it's getting kind of tedious algebraically, then there's probably an easier way to approach it, or maybe you have a mistake. You should go back and look at it. Okay? The math shouldn't be that hard for this exam. It's the vector math is, if you don't know it, then it's going to be hard. But overall, the math shouldn't be that hard. But this isn't that hard, right? Like when you see it written out, it's not that hard. And again, I really prefer that you look at it conceptually. I find that that's a better way to approach it. All right? What else? You want me to skim through? I haven't really done that yet. If you see anything, I can look at it. Let's see, this is the spring 19. The last 5 years of exams are all pretty similar. If you see anything with capacitors, that's not on this exam. Mm-hmm. Yeah, so you'll probably have a question like this. I mean, you have a free response question like this, right? But you'll probably see some questions in the multiple choice. First of all, let's do 17 and 18. So these lines are equipotential lines. I have an electron at point B. So I have an electron right here. What direction does it move? Electrons tend to move uphill. So this will move in this direction towards A, right? So that's the answer there. And if a proton moves from A to B, so a proton moves downhill from A to B. Oh, if you got 17 wrong, then 18 should have clued you in a little bit. What is the energy of the proton? So my delta V is equal to 2 volts, 19 to 17. Notice these are the equipotential lines. It's moving from 19 to 17. Delta V is equal to energy over charge. And so my energy, I'm going to call it my kinetic energy, is equal to 2 volts times the charge, which is a proton. That's 1.6 times 10 to the minus 19. And so it's 2 volts times that, which is a 3.2 times 10 to the minus 19.
So if it was asking what is the energy of the electron?
If it was an electron, it would be the same answer. Oh, of the electron?
Because like,
It would be the same answer.
well, because when you're doing, you don't make the V, it would be -2 because you're doing.
Remember, energy can't be negative because it's a scalar quantity. When we're talking about work and stuff, then we can talk about negatives. But yeah, energy would just be no positive or negative attached to it. All right, y'all? Other things that y'all want to look at? Look, this 17, 18, and 19 actually is a lot like your free response. If you look back where I don't have the free response, you'll find multiple choice questions that are like the free response. That's what I've done is I pulled questions out of the multiple choice that I think are more important and make them for you for free response. And that's why I tell you what they are, because I think they're kind of important. All right. No questions? Is that it for today? Feel okay? All right. Well, look at the old exams, practice those. That's your best indicator of how you'll do. So you should be able to sit down for an hour with no help and work through one of those old exams. And if you make an A on it, then you're probably going to make an A on the exam.